Hi everyone, welcome back to 𝗕𝗂𝘂𝗶𝘁𝗵, broadcast from SobolevSpaces. In this video, I'm gonna talk about connection between data and directed acyclic graphs. We call them DAGs. The Markov assumption, the joint probability for all variables, and associations implied by DAGs. These are the three main things in today's lesson. Over the next chapters, you will learn that immediate causes render conditional independence between variables in DAG. You also learn that with each node we associate a conditional probability, and how their product determines the joint probability for all variables in DAG. Make sure you stick around until chapter 4. There will be examples to help you. And don't miss the takeaways at the end. Data present themselves as joint distributions of variables. With enough observations, we can count how many times each combination of variables' values occurs. Then we divide the count by the number of all observations and get their joint probability. If we only consider one variable, we get a marginal probability for its values. What does the ratio of the joint to marginal probability gives us? The conditional probability. It describes the occurrence of one variable when all other variables happen to have a particular combination of their values. In fact, it's a statement of dependency in probabilistic terms. We use conditional distributions to get the expected values of one variable given other variables. But you can notice that dependency graphs also show how variables depend on each other. Do you see the arrows linking two nodes? They show the direction of their dependency. And it's quite common that several arrows land in the same node. Say the outcome has arrows coming from treatment, age, and coexisting condition. It means that the outcome is dependent on all these variables, not just the treatment. So now we have this striking parallel between conditional probabilities and dependencies encoded by the graph. The network of dependencies comes from the expert knowledge. Conditional probabilities could be estimated from data. Many interpret graphical dependency in DAG as conditional probabilities. You see, among all the variables in the graph, only some have their arrows landing in the variable of interest. It gives us a direct indication for selection of conditioning variables. We condition on immediate causes. And that's the Markov assumption. Immediate causes of a variable render it conditionally independent of all other variables, with one exception: the immediate effects. Let's sort out our terminology. We use kinship language to describe relationships between variables. We read the dependency graph like ancestral family tree. Immediate cause is a parent. Immediate effect is a child. Distant causes are ancestors, and distant effects are descendants. Now, we can define directed acyclic graphs using this language. It's a causal diagram in which no variable is an ancestor of itself. Do you know what is even more amazing? The Markov assumption links DAG to the joint probability for all variables. In probability theory, the joint distribution describes covariation of several variables, and it is a product of their conditional probabilities. Let's see this on paper. In this diagram, M1 and M2 are parents of X. Nodes A and B are ancestors. Let PA sub X denote all parents of X. Arrows landing in X define conditional probabilities, and the Markov assumption asserts each variable's probability depends on only its parents. Their product determines the joint probability. If variable has no parents, no incoming arrows, we use its marginal probability. Recall that the graph is directed and acyclic. No variable is an ancestor of itself. No sequence of arrows get us to a starting point. but arrows place variables in some order of conditioning. This ordering assigns each variable to a set of conditioning variables. In probability theory, this assignment is called factorization of the joint probability. Why is it exciting? Well, the graph tells us all the dependency we need to know. The graph also tells us what we should ignore. We don't have to find the probability given all other variables. Instead, for each variable, all we have to find is the probability given its parents. Indeed, if the graph shows that some variable doesn't have parents, we don't have to estimate it conditional on anything. We just find its marginal distribution. And this brings the notion of exogenous variation. Here is one of the least discussed assumptions of acyclic graphs. All dependencies are deterministic. That's right, randomness is injected through exogenous variables. This is the variables without parents, but they are not orphans. Early literature placed all attention on linear equations. Traditionally, they model dependency using deterministic equations plus the error term. Each equation links variable with its parents, and the randomness comes through the error terms. This approach has a name: structural equations modeling. SEM, Sam for short. In his seminal 2009 book, 𝗕𝗶𝘂𝘶𝗵 goes further. He introduces non-parametric equations. This means we don't specify exact formulas. He argues non-parametric structural equations are capable of finding causal effects. You can check out details on my website. Connecting the DAG structure to univariate conditional probabilities is a major leap forward, but it comes with a cost. The cost is a heuristic called faithfulness assumption. It asserts the joint distribution contains no independencies other than implied by DAG. The difference between two assumptions is telling. The Markov assumption says certain conditional independencies will be in the graph with a particular structure. The faithfulness assumption says those independencies only exist in the graph with a particular structure. This moves us to the realm of DAG implications. In previous chapters, I talked about implications for statistical analysis. And it's great to be able to choose variables for regression models. Implications for the causal reasoning are even more important. And this has to do with conditional independence. Pick any two variables a and b, where b is not a parent of a. Consider the probability of a given its parents, and b. There are two possibilities. One, b is not a descendant of a. In that case, a and b are conditionally independent. Alternatively, b is a descendant of a. Then, in general, they are not independent, even given parents of a. This brings us again to the meaning of arrow. Arrows imply association between variables. Due to immediate effects, the association can be checked empirically when we compare probability of one variable across the values of conditioning variables. Absent arrows imply marginal independence. We check this by comparing the joint probability with the marginal probabilities. If occurrence of two events is coincidence, then the value of their joint probability coincides with the product of their marginal probability. Let's get a better grasp of relations in DAG through example. This graph encodes the following assumptions. X is not a cause of U, and U is not a cause of X. X and U are immediate causes of Y, and Y is immediate cause of Z. And here is independencies implied by this DAG. X and U are marginally, unconditionally independent. X and Z are independent given U, and U and Z are independent given Y. This figure has 4 DAGs. Each shows dependencies among 3 variables. The first three graphs have the same probabilistic interpretation. X is independent of Y given Z, but they have totally different causal dependencies. The direction of arrows is our guide here. Z is either common cause or a mediator. The probabilistic interpretation is only different in the fourth DAG. Do you see two arrows pointing at Z? This indicates that Z is a common effect of X and Y. Now, before we move to the end of this video, please think about the probabilistic interpretation of conditioning on a common effect. Pause the video and complete this sentence. X and Y, given their common effect Z, are... Did you conclude X and Y are dependent? That's awesome. Advances in causal inference led to a fascinating discovery: connection between directed acyclic graph and the joint probability for its variables. Let's recap. DAG depicts the dependency of multivariate data. And data presents themselves as joint distributions. Main message here is the Markov assumption that links the dependency structure of directed acyclic graphs to data. It connects the joint probability for all variables in DAG to their conditional probabilities. Make sure you review examples in the last chapter. It'll solidify your understanding of the implications encoded in DAG. Now you're all set for causal inference with directed acyclic graphs. Keep on watching.